Hello, Chem 1B. This is Chapter 14, Lecture Video 7. And now we're going to kind of take a different tact. So for the last couple lecture videos, we've been talking about how concentration and how rates are affected by concentration and all that. Now we're going to talk a little bit more about how temperature affects our rates of our reaction. And in order to do that, we have to talk about the collision model. And really, this is what's happening in a reaction at like the molecular level. Like if you're like kind of riding a molecule, what would be happening to you as the reaction occurred, right? So one of the things you got to think about here is that the collision model states that in order for a reaction to happen, the reactants, molecules, need to collide with each other, physically collide with each other in order to have a reaction occur. Now, there are three factors that result in a successful collision. In other words, when these two things collide, we need three things to kind of be correct in order for us to have a successful reaction, right? One of them isn't really about having a successful reaction. It's about how often successful reactions occur, and that's concentration. We've spent a lot of time talking about how concentration affects rates of the reaction. Now, the reason why it affects them in the way it does is because the higher your concentration, the more molecules you have present in which that could collide, right? The higher your concentration, the more molecules present, the more likely these molecules will collide with each other. If you think about like a mosh pit, right? You're going to have a lot of collisions there because there's a high concentration of people all moving really quickly around in a pit. If you've ever been to a concert at least. So we're not going to spend a lot of time talking about concentration. We're going to spend time talking about the rest because we've already spent quite a bit talking about concentration. And the other two factors are orientation and energy. And so we're going to spend quite a bit of time discussing these in this lecture video. So one of the things you have to understand about molecules is they are not spherical. So let's talk about orientation first. They have shapes, as you learned in Chem 1A, right? Vesper with the molecular geometries you learned. Reactions are only going to occur when the right pieces of the molecules collide with one another. For instance, I have this picture, right? We have this green ball here colliding with the red ball. And in the collision, they collide, and then they just bounce away. Nothing happened here, right? We had a green ball by itself. We had a red, blue, and green ball by itself before the collision. We have them after the collision. This is an ineffective collision due to orientation. The green ball collided with the red ball, and the red ball, or red atom in this case, probably a nitrogen, by the way, or oxygen, just wasn't the right place. There was no reason for those two to react with each other. But maybe they collide in a different place. Same two molecules. We just rotate this molecule around to get it to this, where the green is now hitting a green atom, probably chlorines. And look at this. We have a collision between these two. Then this guy jumps off that way, and that guy jumps off that way. In other words, these two break apart here. So this is what it means to have the correct orientation. When you have a collision, you're only going to have the two things react if the correct pieces crash together in the collision. Now, the other bit here is going to be energy, but let's look at NaCl, right? So here's NaCl. We have O here, we have N here, we have Cl there. We have two of them. They're both reacting to each other. There are a number of different ways these two things could collide, and there's really only one that's going to lead to a reaction, like here. You can see, hey, if the blue balls collide, the two, wow, they changed the color coding of this from the first picture to the second picture, whatever. If the two blue balls collide, nothing happens. If the blue and the green collide, nothing happens. If a green and a red collided, nothing would happen. A reaction is only going to occur when we have a green ball colliding with a green ball, or in other words, a Cl atom colliding with a Cl atom. This leads to what we call as the orientation factor. Now, the orientation factor is really just based on, hey, percentage-wise, how many times do collisions actually have the correct orientation? Now, the bigger and more complex the molecule, the smaller your orientation factor will be, because there's a lot more places that they can collide, and typically there's only one place that's actually going to be a successful orientation. So let's talk about energy. You need enough energy to break and form bonds, right? So if we have two things colliding with each other, we need to get over that activation energy barrier that we talked about in the first slide of this chapter, right? So here's our reaction coordinate diagram. And if our two reactants collide and they don't collide with enough energy, they're not going to have enough energy to get up over this thing to break our bonds and form new ones, i.e. form products, have a reaction occur. Now, there are a couple things to these coordinate diagrams that you kind of need to be able to label. The difference in energy between the level of the initial reactants and the top of this curve is what we'd call the activation energy. Activation energy is the energy needed for a reaction to actually successfully occur and have the collision produce products. Now, if you get to the very top of this activation energy barrier, you reach what's called a transition state, where like if we have like X and Y, and X is attached to, I don't know, M here, when this guy starts to collide with this guy, we start to see that these guys are starting to form a bond, and this one is starting to break up, but not completely yet. This is what we call a transition state, where the bonds aren't completely broken or formed yet. And we're kind of in this in-between state where X is kind of attached to Y, and it's kind of breaking apart from M, but it's not fully either, so it's connected to both kind of very loosely. This is a transition state. If we went from the level of the products up to the top, this is also an activation energy barrier, but it's the reverse activation energy. So we have an activation energy in the forward direction for the reaction going to products, and we have a reverse reaction that's possible here, usually going from products back to reactants. They usually have different activation energies. As you can kind of see here, the reverse activation energy for this diagram is much larger than that of the forward. So the actual difference between the level of the reactants here and the products down here is actually your delta H, your enthalpy of the reaction. This is the overall release or absorption of energy that occurs every time the reaction happens, which is really what delta H is mostly defined as. So how can we get more energy in order to get over the barrier? Well, the simple way to get reactants to have more energy is raise the temperature. Right? If we raise temperature, everything's going to have higher kinetic energy, meaning they're moving faster. They're going to collide with more energy, and the reaction will happen faster. So as we increase temperature, reactions are going to go faster because more and more of our reactants are going to be able to get over the activation energy barrier. So just to kind of reiterate, you can't just have enough energy or you have the right orientation. You have to have both of these things present at the same time in order for a collision between two things to successfully occur and form products and have a reaction. So for instance, only collisions that are going to have both the right orientation and enough energy are going to result in reactions. So I'm going to show you, I have these different molecules here. They're all going to collide with each other in different ways. So if we look at the first collision, they collide, they bounce off. They had quite a bit of energy there. They were moving pretty fast. They had enough energy. They did not have the correct orientation though, so there was no reaction. We saw the same things bounce away that came in. In the second one, correct orientation, not enough energy. They were moving much slower, right? So that also results in no reaction. Only when we have both the correct orientation and enough energy are we going to have a reaction. So let's look at the third and final collision here. Whoa, look at that. They collided with enough energy. They bounced away, having reacted, right? Now we have 2 red balls on this side and 2 green balls on this side. We created new molecules. This is because they had both the correct orientation and enough energy, which is the only time we're going to get a successful reaction out of a collision. All right. So just to kind of think about this in terms of K, how does energy actually affect our equations? Well, increasing the energy, what it does is increase our rate constant. And this doesn't need to be for a first order reaction. This one is because we have inverse seconds, which is a first order rate constant units. But this could be for any rate constant. It doesn't matter, first order, second order, third order rate constant. They're all going to increase with temperature. And as you can kind of see here, they do so exponentially. As temperature increases, the rate constant increases dramatically. And if the rate constant increases, our rate of our reaction also increases. And so we're going to talk about the equations and the mathematics in all of this in the next lecture video. So if you have any questions, please let me know. And yeah, have a good day.